Title of this is Visualizing Non-Rectangular Beams. And I put the word non-rectangular because I think it's encompasses a lot more than just T-beams. I mean, sometimes we do get creative and we have other shapes. And so want to acknowledge my co-authors on this. Anahid, again, is one of my co-authors. And then Fred Meyer from the United States Military Academy is also a co-author on this paper. And so just a quick overview, kind of the same setup as last time. Non-rectangular beam theory, just want to touch on that a little bit, which will include some struggles that students tend to have. Briefly go over the pedagogical approaches that we use, and then look at the two methods with 3D visualizations and again, the physical models, and then just a few lessons learned that we've looked at over the years. So to start off with, what I do with the equivalent rectangular stress block is I take that a step further after doing the styrofoam block, and I use skeleton files, right? So you've heard a lot about that already. And so I will provide a lot of these 3D drawings for students, and then we'll go in and we'll actually label things. So a lot of the labels that you see right now would not be there. And I like to do that because students get intimidated when they have to do a lot of the 3D drawing on their own. And so, you know, I'm not testing them on their artistic ability. I want them to understand and be able to visualize things. And so the way that I do this is I visualize things. You can kind of think about this as the styrofoam blocks that Anahid had. It's just a virtual version of that. And for the rebar, instead of drawing the circles, I just lump it together as one big rectangle. And so looking at this, if we go through that same process, it's a way to visualize the equivalent rectangular stress block, right? So looking at, we're taking the compressive force as 0.85 F prime CAB. We're taking the tensile force as ASFY, assuming the steel yields. We set them equal to each other, and our only unknown in that equation is going to be A. And I think that's another point to drive home when you're getting into flexural analysis and talking about it. And for a rectangular beam, it's pretty simple, right? So we can do that. Then we go check to make sure the steel yields that our assumption was true, and we can continue to calculate our nominal moment capacity. But when things get a little bit funky, and this is overdoing it a little bit here, but when you have a non-rectangular beam, you can't do that anymore. But what a rectangular beam is simply 0.85 F prime C times a compressive area that just happens to be equal to A and B. And so I backtrack when I get to non-rectangular beams and present it in that way to students. That really what you're doing here is you're solving for an area that's needed in compression to offset your resultant tensile force, regardless of what shape that is. And we want to be able to break that shape down into little shapes that we can work with. I mean, if we wanted to, we could find the centroid of this, we could title it as Y bar, and we could progress through calculating the nominal moment capacity as the distance from the tensile steel to the centroid of that shape. Now, is that very efficient? Probably not, depends on the shape. So we tend to break it down into multiple compressive forces. And the key here is making sure that students understand that it is the summation of the compressive forces has to be equal to the resultant tensile force. And so just with that said, a couple of mistakes that students tend to make. The one that I see a lot is they use a constant width, whether that's B, whether it's BF, B effective, BW, whatever. If it's going to be wrong, they're gonna find it, right? They're going to find one of those to use to calculate it wrong when they're calculating the depth of the equivalent stress block for a T-beam or a non-rectangular beam. The second one is that they assume the moment arm is D minus A over 2, and they run with it. And they calculate the nominal moment capacity as ASFY times D minus A over 2 because that's what they were taught when they did rectangular beams. And then lastly, they calculate the resultant compressive force at the top of the flange section, even if the moment demand is negative. And sometimes they even use the incorrect area of steel when the beam is doubly reinforced. So maybe you have a negative moment situation, but they're still using the rebar in the bottom of the beam to calculate that capacity. And so it's important for them to understand these differences with non-rectangular beams. So the pedagogical approaches in this, again, kind of seems like a lot of us are doing skeleton files nowadays. And if you've never done that, some people are kind of hesitant to do it. but it actually can allow you to either spend more time on topics in class, or it can allow you to cover more material in a semester, because you spend less time writing on the board, students spend less time writing on their paper, and more time paying attention to what you want them to understand. If you were like me in undergrad and were a little bit OCD about your drawings on the page and they had to be perfect, then you look up and didn't hear what the professor said. So it kind of helps with a lot of that. Physical artifacts, so similar to what the other presentation had. And then the last one here, I would say, is peer discussion. So students explain topics to one another, they share their notes, and or they ask each other questions. And so the references for that, if you're interested in seeing those, you can dig into those a little bit more. The objective for this first one, looking at the 3D visualizations, is to determine the depth of the equivalent stress block and calculate the nominal moment capacity for a series of non-rectangular beams with the same amount of tensile reinforcement and distance from the extreme compressive fiber to the centroid of the tensile reinforcement. And the reason for that is so they can see the difference in behavior of beams. And so what I'm going to show you here is just a couple of examples of the way that I would present this in class. These are filled in, but in class they would be blank, and the students would have to calculate this on their own. So for example, we go through a rectangular beam, and in each one of these cases, D is 21 inches. I didn't label it on the 3D ones because they get a little bit confusing with too much on them, but D is 21 inches for every one of the examples. And so in this case, the students know what to do. They can jump in. They can probably do this in about 5 minutes. They calculate their depth to the equivalent rectangular stress block. They convert it to the depth of the neutral axis. They calculate their strain in the steel. They see in this case that this one is a tension controlled beam. It's greater than 0.005. They calculate their nominal moment capacity, and we move on to the next one. Now, what I generally do in class is I give them, I break them up into groups, and I will give them each group a different beam, and they have to calculate the capacity. But the thing is, I don't tell them how to do this. So the only thing that I've presented up to this point is you have to have an area of concrete that's in compression when multiplied by 0.85 F prime C will offset T. And I use pretty much a whole class period for this. So there's a lot of peer discussion. They're working in groups, and they have to kind of derive their own equations. And the reason I do this rather than just coming up with one simple T-beam is because students will most definitely try to apply a single equation to just about any case. And so it's important for them to derive their own equations for different shapes. And so for this one, they go through, and in this case, the way I look at it is I treat it as two positive areas. You can do this one a little bit different. You could treat it as one big positive area and subtract out two negatives. It works just the same. Sometimes in class, I'll have students do it both ways, and then we'll get the answer and we'll compare them if they're both the same. Now, the thing I like about this too is, again, we're keeping the tensile reinforcement the same, the D value the same. You go through this process, you see here that all of a sudden my A value is small, my C value is smaller, and my strain and my tensile still got a lot larger. I mean, it almost tripled because we reduced the A, we reduced the C values. And then when we go through to calculate the nominal moment capacity, this is where we have a long discussion about, all right, you can't just take the resultant tensile force times D minus A over 2, because the centroid of that compression zone is no longer located at A over 2 from the top of the beam. And so we go through that discussion and talk about breaking it up into multiple areas so that they can do that. I tend to get a little creative with them to make sure that they can apply this concept. You have to be careful with this though, because with T-beams, the equivalent rectangular stress block is made for rectangular sections. And so if you get less area on the top, you can actually get a little unconservative. It's not a huge difference, but a little bit unconservative with your numbers. And so with this one, for example, there's a couple ways to do it, but I like the option of taking one large compressive area and then subtracting the two smaller areas, making them negative moments. Either way you do it, it's going to work out at the end. And this time they see that their A and their C values get larger because there's not as much going on at the top of the beam. Their strain, their steel gets lower. but calculating their nominal moment capacity, they're still having to break that up into, individual components and calculating that. And then the last one here that I do, I get really creative with them, is a kind of like one that looks like a house. I've also given them a completely triangular, or actually just gave a test this afternoon during the first session, and it had a trapezoid on it to see if they could do that. So you can get pretty creative to see if they really understand the concepts. In this case, there's, again, it's using a positive and a negative area scenario where they take a positive rectangle and they subtract out two triangles. Again, it's a comparison to show them what happens to A and C as you change and manipulate the cross section. They get a smaller strain value, but again, they're still having multiple resultant forces when they're calculating the nominal strength. And then what I like to do at the end is actually compare everything, right? So the neat thing about this is the T didn't change, the summation of the compressive forces didn't change, but everything else did, right? Because we changed the cross-sectional shape. Your A values are going to change, your C values are going to change, your strain and your steel is going to change, your nominal moment strength is going to change. So we can even use this to talk about efficiency and to show that the T shape is actually a very efficient cross-section, because we can make it more ductile, and we can also increase our nominal strength. And so that's the visual approach. Now, for the physical models, and again, Anahi briefly talked about this in her presentation earlier, but the objective is to create three-dimensional models associated with different cases for a flanged beam to help students distinguish the differences and calculate the flexural strength correctly. And so for this one, looking at case one, this is the traditional T-beam, right? So this is similar to what I did with my visual examples. Case one is a positive moment with enough reinforcement that the stress block extends down into the web. So you're still going to have two different compressive forces. In this case, you can see there on the right, everything is labeled. You've got the stress block that is getting down into the web, and we can explain to students that there's enough reinforcement to require that area of compression to get down into the web. The second case is when you have positive moment without enough reinforcement for the stress block to extend down into the web. This is an example where it's just a rectangular beam. And I've done a thing in class before where I've given them a problem like this, and they will undoubtedly plug in numbers to the T-beam equation to solve for A, and they get a negative A value. And they wonder, they can't figure out why they get a negative A value. And I ask them, well, did you check to see if it was rectangular to begin with? And so that's one of the first steps, right? And so it's important for them to visualize that just because it looks like a T, also doesn't mean that it's going to act like a T. And then lastly, the scenario when you actually have a cantilever beam that looks like a T, but in this case, everything is flipped upside down. So your compression zone is at the bottom of the beam, and we have to use the reinforcement located in the top of the beam when we're calculating that nominal strength. And so again, just kind of visualizing those concepts for them, because it's really hard to grasp this when you simply see it in 2 dimensions on paper. And so just to hit some lessons learned here, the analysis of different cross sections highlights the effect of compression zone shape on depth of compression, strain in the tensile reinforcement, and nominal moment capacity. Or in other words, we can really have an in-depth conversation about ductility and flexural strength. The 3-dimensional models, whether that's virtual or physical, do help students to visualize the concepts for the analysis of beams with different cross sections. And then lastly, the models take time, whether those are physical or virtual. They do take time to create on the front end, but the prep time decreases significantly after the first offering. So whether you're in a shop making your physical ones, or you're on PowerPoint, which is where I draw all those, drawing those out, it takes you a little time on the front end, but it is worthwhile to the students in the long run.